About 2 weeks ago, I tested my largest rocket motor yet. It's called MEGAx, and it was designed to produce around 500 pounds of thrust. And as you'll see later, it did quite a bit more than that. Just like this test pushed MEGAx to its limits, it also pushed me to mine. This is by far my most difficult test yet, and a lot went wrong along the way. If you're interested in the test itself, definitely check out the test video. After seeing what this motor went through, the big question is, how did it actually hold up? MEGAx took a serious beating, and I'm really excited to tear it apart and see what survived. I've gone through the test footage frame by frame, analyzed the data, and carefully inspected every major component of MEGAx. In this video, we're going to disassemble the motor and see what worked, what didn't, and what this static fire taught me. If you're new here, MEGAx is a reusable, high-powered solid rocket motor I've been developing over the last several months. It's designed to produce around 500 pounds of thrust with a total impulse of around 5,000 newton-seconds. It's by far the most powerful rocket motor I've ever built and tested. This motor uses a custom aluminum casing, a graphite nozzle insert, and is fully instrumented to capture thrust, pressure, and temperature during the static fire. The goal with this test wasn't just to produce thrust, but to push the design harder to see how the hardware, seals, and structure held up under real conditions. And now that the test is done, it's time to see what MEGAx looks like from the inside. Looking at the motor on the test stand, everything held up really well. Aside from some mud and debris on the stand, it's practically untouched. All the adapters on the bottom of the stand were able to take the thrust without bending or deforming, and overall, this stand worked exactly as intended. Now it's time to focus on the motor itself. Before disassembling anything, I wanted to visually inspect the outside of the motor. Right away, you can see that both the nozzle and bulkhead have a noticeable gap from where they seat against the casing. There is normally a very small gap here due to the radial bolt tolerances, but this is much larger than expected. That's something we'll keep in mind later when we look at the casing in more detail. For disassembly, I start by removing the 8 radial bolts that hold the bulkhead in place. This was not easy. I originally installed these bolts using a screwdriver, but I quickly had to switch to an Allen wrench just to get enough leverage to back them out. Once the radial bolts were out, I tried to remove the bulkhead, but it was still extremely tight. This bulkhead really did not want to come out, and there wasn't much surface area for me to grab onto. I could have tried pulling on the pressure transducer to get it out, but that would risk damaging it. So instead, I moved on to the nozzle. The 8 radial bolts on the nozzle were just as difficult to remove as the ones on the bulkhead. And once those were out, you could really start to see how much the casing has deformed under the pressure. The nozzle itself was also very difficult to remove, but because of its shape, there was at least more area to grab. I ended up needing to place the motor on the ground, sitting on top of it, and slowly working the nozzle out bit by bit. Once I had it mostly free, I moved the motor onto the bench and pulled the nozzle out all the way. There's already a lot to unpack here, and we'll come back to this after the motor is fully disassembled. With the nozzle out, removing the bulkhead is much easier. I was able to fit a 1-inch dowel through the motor and carefully tap the bulkhead from the opposite side. You can see that there's a bunch of slag from the propellant at the bottom of the motor that solidified. This essentially acted as a hard glue and was a big reason the bulkhead was so hard to get out. Now that the motor is fully disassembled, the first component I want to take a closer look at is the nozzle. The nozzle experienced the most extreme conditions during the test, and it tells us a lot about how MEGAx actually performed. Before cleaning it, you can clearly see the slag buildup on the converging side, and especially on the diverging side of the nozzle. This is very common with sugar rocket motors and isn't really a major issue. The slag actually cleans off very nicely with just some warm water. And before cleaning it, it's also a great visual to check that there's no debris across the first O-ring. Combined with the fact that there's no visible leaks in the test footage, this shows that the O-rings worked perfectly. This sealing interface is something I really focus on in my designs, because it's one of the most critical parts of the entire motor. If this fails, there may be no more rocket motor. Before I look at the rest of the nozzle, I went ahead and cleaned off all the slag off of the nozzle. Now looking at the graphite insert, it held up amazingly well. I was only able to find a few areas that the graphite slightly chipped away, but overall I'd be very confident reusing this insert for another test. Looking at the diverging section of the nozzle, the aluminum part also held up perfectly. One thing I did notice though, that there was a larger gap on the transition between the graphite insert and the aluminum. There was a very small gap before the static fire that I filled with RTV, but now it's visibly larger. It's almost like the graphite insert was pushed upwards. After thinking about this for a bit, what I concluded is that aluminum has a much higher thermal expansion rate than graphite. So as the nozzle heated up, the aluminum expanded, and due to the geometry of this area, it likely pushed the insert upward slightly. This isn't ideal, but it's actually much better than the aluminum expanding and cracking the graphite insert. But overall, I'm honestly really surprised at how well this nozzle held up. Before disassembling the motor, when I was analyzing the test footage, the start of the burn appeared to be very dark. I originally thought this was a graphite insert being eroded and injected into the exhaust. But after seeing the nozzle insert, that was clearly not the case. Now, looking at the radial bolt holes on the nozzle, they definitely took a beating. You can clearly see where the bolt holes deformed under pressure. This was partially due to the bolts being slightly shorter than I would have liked, and also due to the chamber pressure being much higher than expected. As some of you may already know, many of these pressure-related issues were caused by cracks in the propellant grain. The coring rod I used for casting was very difficult to remove, so I had to tap it with a hammer. That introduced a number of small cracks in the propellant, which increased the burn surface area and resulted in a higher chamber pressure. Because of how long it takes me to cast the propellant, and in order to keep this motor on schedule, I decided to test it anyways. Knowing that the pressure would likely be higher, I added a higher factor of safety on the radial bolt holes on the casing. That higher pressure didn't just affect the hardware inside the motor, but it also showed up clearly on how the exhaust behaved during the test. A lot of people noticed that the exhaust plume appeared to be underexpanded, and that observation is correct. An underexpanded exhaust means that the pressure of the exhaust gases leaving the nozzle are still higher than the surrounding atmospheric pressure. Ideally, you want the exhaust pressure at the nozzle exit to be as close as possible to atmospheric pressure. In this test, the exhaust is underexpanded specifically because the chamber pressure inside the motor was much higher than expected. This means the motor was producing a lot of thrust, but it wasn't doing it as efficiently as it could have been. Now, let's look at the casing and see how it held up. Right away, you can clearly see some damage around the radial bolt holes. This was again due to the chamber pressures being much higher than expected. When designing MEGAx, I intentionally chose a thicker casing. While it does add some weight, it allows me to safely run this motor at higher pressures and also position the radial bolt holes closer to the edge of the casing. On one of my previous motors, SN3, the radial bolts of the nozzle actually tore out of the casing. With how large MEGAx's nozzle is and how much thrust it produces, this simply cannot happen here. That's why, like I mentioned earlier, I added a large factor of safety when designing the radial bolt hole tear-out strength. Aside from the deformation around the bolt holes, the casing itself held up very well. For this test, I also added an Arduino with thermocouples to measure the outside casing temperature. My goal here is to eventually reuse the casing, but aluminum can lose its temper at high temperatures, which significantly reduces its strength. This system was designed to track the casing temperature so I could determine whether the casing would be safe to reuse after the test. Unfortunately, the system didn't work and no temperature data was recorded onto the SD card. This was most likely not related to the data not being recorded, but when attaching the thermocouples with pipe clamps, I tightened them down too much and crushed the thermocouple head. Before the next test, I'll figure out what went wrong with this system and make any necessary modifications. Next, let's look at the chamber pressure and see what this motor was actually doing during the burn. When simulating MEGAx, the model predicted that the maximum chamber pressure would be around 650 psi. So when it came time to choosing a pressure transducer, I decided to go with a 1600 psi sensor. At the time, I did not expect to get anywhere close to that limit, but I was very wrong. Looking at the pressure data, the transducer actually maxed out at 1680 psi. I would like to think the pressure did not get much higher than that, but with the sensor getting maxed out, there's no way to ever know. And apparently, I didn't learn my lesson because on SN5, I also ended up maxing out the pressure transducer. For MEGAx V2 static fire, this is something I'll definitely be correcting and using a much higher rated pressure transducer. Next, let's take a look at the final major component, the bulkhead. The bulkhead had a significant amount of slag buildup, along with a small spot that was pretty interesting to see. Just like the nozzle, this slag washed off very easy with just a bit of warm water. Overall, the bulkhead held up very well. The O-rings worked perfectly and did not allow any gas from escaping during the test. There was still some deformation around the radial bolt holes, but it was less noticeable from what we saw on the nozzle. The side of the bulkhead that was exposed to the combustion chamber showed slight discoloration, but no physical damage at all. One thing I did notice was some small tears around the O-rings. I also saw the same thing on the nozzle. My best guess is that this happened during disassembly when pulling the nozzle and bulkhead against the slightly deformed radial bolt holes in the casing. This isn't an issue because the O-rings will always be replaced in between tests. With the hardware now fully analyzed, let's take a look at the data from the load cell. These numbers were honestly very surprising. MEGAx was originally designed for 500 pounds of thrust, but during its first static fire, it actually produced a peak thrust of 1,787 pounds. That's a 246% increase over the design target, and it was almost entirely due to the chamber pressure being much higher than expected. To better visualize this, I put together a table comparing the simulated performance to the actual test data. Looking at the total impulse, MEGAx produced 4,267 newton-seconds, which is only 13% lower than the simulated value of 4,930 newton-seconds. The specific impulse also came out fairly close to the simulation at 114 seconds, which is about 11% off of the predicted value. The total burn time came to 2.96 seconds, which is only 5% off from the simulation. And the average thrust was 1,441 newtons, which is 18% off of the predicted value. Overall, these numbers are very solid for the first iteration of MEGAx. It's also important to note that this test was far from ideal. Because the cracks in the propellant grain, this motor was operating outside of its intended conditions. A lot of people suggested that I should not test this motor at all and recast the grain. But honestly, I learned a lot through this test. An iterative design often teaches you much more than waiting for everything to be perfect. For example, based on what I learned here, MEGAx V2 may intentionally be designed to run at a slightly higher chamber pressure. Without this test, I wouldn't have the data or confidence to make that decision. Sometimes, even when conditions aren't ideal, you need to move forward with the test, and in this case, that decision paid off. Soon, I'll be starting the design process again for MEGAx V2. There's a lot I learned from the static fire, and all of that will be applied directly to the next iteration of this motor. If you want to follow along with that process, make sure you're subscribed and stay tuned for future videos and live streams. In the next video, I'll be doing a full cost breakdown of the entire MEGAx test campaign. I'm very excited for that one because even I was very surprised with the final number. I also offer channel memberships where I post bi-weekly update videos and behind the scenes content. Memberships start at $1.99 and it's a great way to support these builds. Other than that, I really hope you enjoyed this video. Please subscribe, comment, and like, and I'll see you in the next one.